Welcome back to Talk Tensors. So, we got a really interesting paper sent to us, and, it tackles a pretty fundamental issue in machine learning, this kind of like tension, right, between how well a model performs, how accurate it is, and how easy it is for us as humans to grasp why it's doing what it's doing.
Yeah, absolutely. It's a really core issue, and it's becoming increasingly important as these models get more and more sophisticated, and this paper is particularly interesting because it looks at this trade-off, right? This accuracy versus interpretability trade-off in the very specific domain of natural language processing, NLP, and specifically how well different models can predict, those product ratings you see, like on Amazon reviews, from the actual text of those reviews.
Yeah. Which, that's huge for any business or anyone who's trying to, make sense of customer feedback, right? That impacts, so much of what people are trying to do these days.
Oh, absolutely. Understanding customer sentiment, right, is so critical for, product development, marketing. You name it,
Exactly. And what's really cool about this paper, at least from my perspective, is how they really try to put a number on this very, very fuzzy concept of interpretability, right? They come up with this composite interpretability score, the CI score, to compare different models head to head, even some really novel combinations of models. And what they actually find is that common assumption we have that, the better a model performs, the less we can understand it. Well, it's not always true. It's not as straightforward as we might think.
That's exactly right. That's the kind of the big takeaway here, challenges that simplistic view, right? They found cases, right, where a more interpretable model could actually do just as well or even, outperform a more complex black box approach. And that makes you stop and think, right? Like, okay, how much accuracy am I willing to sacrifice to actually be able to understand what's going on, right? What's driving these predictions?
Absolutely. So let's dig into that a little bit more, kind of walk through how they actually got to these findings. So basically, they take a bunch of these different machine learning models, right, from very, very simple rule-based systems all the way up to these massive, pre-trained language models like BERT, and they see, how well each one can predict the actual star rating, right, from the text of a customer review. But like you said, the key here is that they're not just looking at accuracy. They're also trying to figure out, how interpretable each model is. How easy is it for a human to make sense of what's going on under the hood?
Exactly. And to do that, to do this rigorously, they set up this really, really carefully controlled experiment. So they used 4 different data sets, right? Each with 10,000 Amazon product reviews. And these data sets, they cover different product categories, things like cell phone accessories, office products, automotive stuff, and even video games.
Nice. So a good mix there. Yeah.
A good range, right?
Yeah.
And to make sure they were comparing apples to apples, right? They cleaned up the text data. They removed all those really common words, those stop words. They removed punctuation, basically just trying to, get rid of any noise that might not be, meaningfully impacting the sentiment or the rating.
Yeah, makes sense. Get down to the meat of it.
Yeah.
So then they took this cleaned up data and they threw a whole bunch of different models at it. So on the more interpretable side, they started with Vader, right, which is basically a set of rules for figuring out the sentiment of a piece of text. It's not a machine learning model in the traditional sense, but it's very transparent, right? You can look at the rules and see exactly how it's making its decisions.
Right. So very, very straightforward. Yeah, and then from there they moved on to those more traditional machine learning models.
Yeah.
The ones that actually learn from data. And these models, they first convert the text into numbers, right? Yeah. Using different techniques. And there's a bunch of different ways to do that. So one of the simplest ways is just counting how often each word appears in a review, right? Okay. And that's called count vectorizer.
Right. Well, so basically just, how many times does the word great appear? How many times does the word terrible appear? That kind of thing.
Exactly. And then, you can get a little bit more sophisticated, right? You can start weighting words by their importance. Yeah. Words that appear very frequently across all reviews, maybe those aren't as informative, right? So this method, this is called TF-IDF. It tries to, downweight those common words and upweight words that are more specific to certain reviews, words that might actually be more indicative of the sentiment.
Right. So it's trying to pick out the words that are really carrying the emotional weight, the ones that are really driving that positive or negative sentiment.
Exactly. And then you can go even further, right? You can represent words as these dense vectors, these lists of numbers that capture their meaning, not just in isolation, but in relation to other words. And this is called word to vec.
Yeah, word to vec. That's one of those, deep learning techniques, right? Where it's learning these really rich representations of words, based on how they're used in massive amounts of text.
Exactly. And this is where things start to get a little bit less interpretable, right? Because now you have these vectors, these lists of numbers, and it's not always clear what each number represents, how it relates back to the meaning of the word.
Right. You can't just look at it and say, oh, well, this number means, happy and this number means sad. It's much more abstract than that.
Exactly. But it's also, it's also very powerful, right? Because it captures a lot of the nuance and the context of how words are used.
Right. So they've got these different ways of turning words into numbers, and then they paired each of these methods with a bunch of different classifiers, right? So, you've got your logistic regression, your naive Bayes, your support vector machines, and even a fairly simple, neural network.
Right. And, they've laid these out from most interpretable to least interpretable based on, what experts in the field generally agree on,
Yeah.
So logistic regression being one of the, simpler, more transparent models. And then as you move towards neural networks, things become, increasingly complex and a little bit more opaque.
Right. It's that black box problem again.
Exactly.
So they've got this nice spectrum of models, right? From very, very simple and transparent to quite complex and a little bit harder to make sense of.
And then to make things even more, interesting and insightful, they brought in BERT. This really powerful pre-trained language model that's been trained on massive amounts of text. It can understand context and nuance in a very sophisticated way.
Yeah, BERT. That's one of the the big names in NLP these days.
Absolutely. It's incredibly good at a lot of language tasks, but it's also very much a black box model, right? We know it works well, but it's very hard to understand exactly why it's making a specific prediction.
Right. So it's great for performance, but not so great for understanding.
Exactly.
And then to make things even more, kind of push the boundaries here, they created these composite models where they actually took the sentiment score that BERT predicted and used that as an extra piece of information for those more traditional learning-based models. So it's like they were trying to, get the best of both worlds, right? The power of BERT with maybe some of the interpretability of those simpler models.
Exactly. And that's where the CI score comes in, right? They needed a way to quantify how understandable each of these models was, especially these new hybrid models that they'd created. So how do you put a number on something as subjective as interpretability?
Right. Because interpretability, I mean, it's not like accuracy, right? Where you can just say, oh, well, it got, 80% of the predictions right. It's much more about, can I, as a human, look at this model and make sense of what it's doing? Can I follow the logic? Does it make sense to me?
Right. So their proposed CI score, it's actually a pretty clever approach. So they surveyed 20 experts in the field, all right? And they asked them to rank those core models, Vader, logistic regression, naive Bayes, support vector machines, the simple neural network, and BERT, right? On how simple they were, how transparent their decision-making process was, and how easy it was to explain their predictions. And they asked for these rankings on a scale of 1 to 5, 1 being the most interpretable, 5 being the least.
Okay, so basically they got these expert opinions, from people who really know this stuff about how easy it is to understand what's going on inside these different models.
Exactly. And then, to actually create the CI score, they assigned weights to each of these criteria, right? So simplicity, transparency, and explainability, they all got an equal weight of 0.2, so 20% each. And then they also factored in the complexity of the model itself, using the number of parameters as a measure of complexity. And they gave that a higher weight, 0.4, so 40%.
Okay, so basically the more, internal knobs a model has, the more complex it is, the lower its interpretability score is going to be.
Exactly. So they combine these expert ratings and the parameter count into this interpretability score, IS, for each individual model. And for those text embedding methods, the count vectorizer, TF-IDF, and word2vec, they assign scores based on the general understanding in the NLP research community about how inherently interpretable these methods are.
Okay, so they basically used a combination of expert judgment and some kind of common sense understanding of how interpretable these different techniques are to come up with these scores.
Right. Right. And then for the composite models, the ones that combine multiple methods, they had this very straightforward way of calculating the CI score. It's basically just the sum of the interpretability scores of the individual models that make it up.
Okay. So if you have a model that's using, TF-IDF to represent the text, and it's using BERT sentiment score as an additional feature, and then it's feeding that into, a logistic regression classifier, you just add up the interpretability scores for each of those components, and that gives you the overall CI score for that composite model.
Exactly. So pretty simple, right? But it gives you this quantitative way to compare how understandable these different hybrid approaches are.
Right. So they've defined how they're measuring interpretability. They've got their models. They've got their data. So what did they actually find? When they ran all these experiments, what are the big takeaways here?
So when they plotted the interpretability scores against the accuracy of the models, what they found was what they called a non-strictly monotonic trend. This basically means, in simpler terms, that the relationship between how well a model performs and how easy it is to understand, it's not a straight line. It's not like one always goes up as the other goes down.
Right. So it's not a simple trade-off.
Exactly. And they found some really interesting outliers, right? Cases where models with, lower interpretability scores, meaning they were actually less interpretable, also had lower accuracy, which, that kind of makes sense, right? You'd think that the more complex models would do better. But then they also found cases where more interpretable models actually outperformed less interpretable ones, which, that was a bit of a surprise.
Yeah, that's really interesting, right? It's not always the case that sacrificing interpretability gets you that boost in performance.
Right. And they specifically called out a couple of things. So they noticed that Vader, that rule-based sentiment analyzer, it consistently didn't perform as well as many of the other models, which, maybe not a huge surprise, right? It's a very simple model.
Right.
But they also saw that when they used word2vec to represent the text and then fed that into a naive Bayes classifier, the performance was also pretty poor.
Huh. So even though word2vec is, it's a more sophisticated technique, it's not always a slam dunk.
Right. And their explanation for this is actually pretty insightful. Naive Bayes, it works best when the features it's looking at are independent of each other. But word2vec, it's designed to capture the relationships and dependencies between words. So the fundamental assumption of naive Bayes is kind of violated, right, when you use word2vec.
Right. So it's like you're feeding it this rich contextual information, but then you're using a model that's assuming that all these words are independent of each other, which they're not.
Exactly, and that can lead to to lower accuracy. It's a good reminder that you really have to think about the underlying assumptions of the models you're using and how they align with the way you're representing your data.
Yeah. You can't just, throw any model at any data and expect it to work magically. You really have to think about how these things fit together.
Right. So they also looked at what happened when they kept the text representation consistent. They used TF-IDF, and they just varied the classification model. And they generally saw that as they moved towards more complex and less interpretable classifiers, things like neural networks, the accuracy tended to improve a little bit, but the differences weren't huge. Often the accuracies were in that 40 to 60% range.
Right. Okay. So even with these more, complex models, you're not necessarily getting, this massive jump in performance.
Right. And then interestingly, when they added BERT's sentiment scores to those TF-IDF based models to create those composite models, they often saw a pretty decent boost in accuracy, highlighting that power of leveraging information from these more complex language models. But they also observed that combining naive Bayes with BERT sentiment scores actually hurt the accuracy.
Huh. So again, it's not a simple, just add more complexity and it'll get better.
Exactly. It's really about understanding how these different components interact, what works well together and what doesn't.
Yeah, it's about finding the right balance. So they did all this modeling, right? They compared all these different models, but then they also, they wanted to dig a little bit deeper into why some models were performing better than others. So they did a correlation analysis, specifically comparing Waiter, that most interpretable rule-based system, with BERT, that least interpretable, deep learning model.
Right, and what they looked at was how well the sentiment scores that these two models assigned to the reviews correlated with the actual star ratings.
Yeah.
And unsurprisingly, BERT showed a much stronger positive correlation, which they believe is because BERT has been trained on, vast amounts of text, including product reviews.
Yeah.
So it's better attuned to the nuances of sentiment in that specific domain.
Yeah.
Whereas Vader, is more geared towards general social media sentiment.
Right. So it's like BERT has seen more product reviews, so it has a better sense of how people express their opinions about products.
Exactly. And their visualizations kind of showed that. Vader's sentiment scores tended to be, more spread out and less directly tied to the specific star ratings. While BERT's scores, they showed a much tighter relationship. They clustered more closely around the actual ratings.
Okay, so BERT is, it's doing a better job of actually capturing the sentiment that's expressed in those product reviews and mapping that to the star ratings.
Exactly. But they also point out that even with a powerful model like BERT, relying solely on sentiment analysis has its limitations.
Yeah.
Right? There were still reviews where the sentiment didn't perfectly align with the star rating. Maybe someone wrote a very positive review. They talked about all the great things about the product, but then they only gave it 3 stars. So there's more to it than just sentiment, right? There's other factors that go into those ratings.
Right. So it's not a perfect proxy.
Yeah.
So to kind of sum up the main takeaways here, for our listeners, this paper, it really shows that when it comes to predicting ratings from reviews, it's not this straightforward accuracy versus interpretability trade-off. More complex models, those black box models, they don't always perform better. And combining more interpretable and less interpretable components, it can lead to some really interesting results.
Exactly. And it pushes us to think beyond just, hitting the highest accuracy numbers and to consider the value of understanding why a model is making certain predictions.
Yeah.
Especially in applications like analyzing customer feedback, where those insights can be really valuable. The CI score, it provides a concrete way to start evaluating models on both of these dimensions.
Right. It's about thinking more holistically about what we want from these models, not just, how good they are at hitting the target, but also how much we can understand about what they're actually doing. So this brings us to our novel notions segment, right? Where we kind of take the findings of the paper and we think about, okay, what are some interesting directions that future research could take, based on what we've learned here. So what are your thoughts on that?
So one really fascinating area, I think, is to make that CI score, that composite interpretability score, a little bit more dynamic. In this paper, they used fixed weights for those different components, simplicity, transparency, explainability, complexity.
Mm-hmm.
But, in reality, in some applications, maybe something like medical diagnosis, the ability to explain a prediction, it might be much more critical than, in a movie recommendation system.
Right. The stakes are much higher.
Exactly. So future research could look at ways to maybe automatically adjust the weights of these CI components based on, the specific context. What are the potential risks associated with a lack of interpretability? You could even imagine a system that learns over time, what aspects of interpretability are most important for different types of problems.
Yeah. So it's like an interpretability metric that adapts to the situation. It takes into account the severity of getting things wrong.
Exactly. And that could be really powerful, right? Because it allows you to really tailor your evaluation to the specific needs of the application.
Right. Not all interpretability is created equal, right? It depends on what you're doing with it.
Absolutely. And another promising avenue, I think, is to investigate this idea of the interpretability cost of gaining, a little bit of accuracy. So building on the CI score, we could try to assign a quantifiable cost, maybe even a monetary cost or a societal cost, in high risk scenarios to using less interpretable models.
Right. So basically putting a price tag on on that black box, right? Saying, okay, well, if we use this model that's really hard to understand, what is the potential downside of that? What could go wrong?
Exactly. And this could lead to this decision-making framework where, you aim for a certain level of accuracy, but you have to stay below a certain interpretability cost threshold. You can imagine regulators using this kind of framework to set minimum interpretability standards for AI systems used in finance or criminal justice, forcing developers to really think about, is that extra, fraction of a percent inaccuracy worth the trade-off in understanding and the potential for hidden biases.
Yeah. Yeah. It's about making those trade-offs explicit, right? And really thinking about the potential consequences of using these very powerful but sometimes opaque models.
Exactly.
Well, this has been a really fascinating deep dive into this whole issue of accuracy versus interpretability in the context of predicting product ratings.
Yeah.
So thank you for sharing this paper with us. And for our listeners, if you wanted to really dig into the details of their methodology and their results, we'll have a link to the full paper on our website. But for everyone else, the big question to think about, as AI continues to advance, how should we as a community balance this pursuit of ever higher accuracy with this crucial need for understanding and trust in these systems? What metrics beyond just accuracy should we be prioritizing? It's something to really think about.
Absolutely. It's a question that's not going away,
Yeah.
and it's one that we all need to be grappling with.
Well, on that note, thank you for joining us for this deep dive. And until next time on Talk Tensors.